Welcome to our first video mini lecture. As a reminder, for each class meeting, I will create one or more video mini lectures, indicate the companion reading from the textbook, and post the activity handout for the assigned material. To prepare for our virtual meeting, I'll ask you to view the videos, supplement with a companion reading, and then work through the activity. You can find all the details on Sakai. This video introduces the idea of a feedback loop. I'll go over a quick refresher on stocks and flows, and then describe how to use feedback loops to understand a system that is not in equilibrium.
So just a reminder where we started at the beginning of Chapter 2, we thought about a systems perspective. And when we say a system, we mean an interconnected set of elements that is organized in some way. And a system can exist at many different levels. So for example, we could think of a farm, a watershed, or the entire planet all as systems. That is, they're made up of these interconnected elements that are organized in some way. The idea of stocks and flows has allowed us to model such systems. We can think of the various elements in a system as represented by stocks, and then the connections between them often can be represented by flows. One thing that we've been interested in our work so far is understanding systems in equilibrium. For example, we've thought about when a system is in equilibrium and what that equilibrium is by looking at when an inflow is equal to an outflow. However, we want to also understand systems that are out of equilibrium and how they behave, and that will be our focus going forward. Let's go back to one of our classic examples from earlier in this semester, the bathtub stock flow model. Here, the stock represents the water in the bathtub. We have an inflow, water coming out of the faucet, and then we have an outflow, water draining out through the drain. As we talked about earlier in this semester, the greater the depth of the water in the bathtub, the greater the flow rate through the drain. We represent this in our stock flow diagram by the red control arrow. We have a plus there to indicate that greater stock levels correspond to a greater outflow rate. When we looked at this example in the past, we were able to create a model of the inflow rate. Generally, we might expect this to be constant at whatever level we set the faucet at. And then the outflow rate, which again is proportional to the amount of water in the drain. And that we modeled by a line in our flow rate graphs. By looking at those graphs, we were able to see where the inflow matched the outflow, and using that determine what the equilibrium point was for the bathtub. One issue we didn't talk about a lot there, though, was the fact that the bathtub is not initially at equilibrium likely. As water pours into the faucet, the depth of the water is increasing because the drain outflow rate doesn't yet meet the inflow rate. Let's take a look at that more carefully. The following graph shows how the water's depth would change over time. You can see up at the top there's a red dotted line. That's representing the equilibrium for this stock flow model. But we can see that the initial bathtub water depth is 0, expecting the bathtub to be empty when we initially turn the water on. And over time, the bathtub depth slowly rises and then starts to level off as the outflow starts to balance with the inflow. So this gives us an understanding of how this bathtub behaves when it's not in equilibrium and how it ultimately does approach the equilibrium for this system. Another important example for us is the temperature of the Earth's surface. We modeled this using the naked model planet, which generated the stock flow model that you see at the top. Here, we thought of shortwave radiation as coming in from the sun, and this represented the inflow to our stock. Then long wave radiation through blackbody radiation represented the outflow. Using Stefan's law, we also saw that the outflow rate was proportional to the temperature of the Earth's surface. That is, the warmer the surface of the Earth was, the more of this radiation going outward that we would have. So this gives us a very similar model to what we saw in the bathtub. Right now, we're in a situation where our system is not in equilibrium. The temperature of the Earth is going up overall. So again, we want to understand under what circumstances systems are not in equilibrium and what will happen to them in the long term. One way that we can analyze systems that are out of equilibrium is by understanding the feedback loops that are present in the stock flow model. A feedback loop exists whenever the level of a certain stock is directly or indirectly affects one of the inflows or outflows for that same stock. That is, we have the stock affecting the flow in some way, and then the flow affects the stock, and this is what's creating the loop in our system.
We'll consider two types of feedback loops. We'll classify a feedback loop as stabilizing or negative if the loop tends to move the stock level in the opposite direction from some set point. That is, if the stock level deviates somewhat from its equilibrium, the feedback loop will tend to cause the stock level to settle back down to the equilibrium. An amplifying or positive feedback loop will have the opposite effect, moving the stock level in the same direction as the deviation. If an amplifying feedback loop is present and the stock level has varied from its equilibrium point, the feedback loop will tend to move it farther away from the equilibrium.
Let's apply these ideas to one of the examples we've already discussed, the bathtub stock flow model. As we saw earlier, we have here a control. That is, the stock level, the water in the bathtub, affects how quickly the water drains out. This creates a feedback loop. The stock affects one of the flows from that same stock. In the diagram below, it shows how, if we are below the equilibrium level, the water level tends to rise and slowly levels off as it approaches the equilibrium level. Similarly, if we happen to have a bathtub stock level that was above the equilibrium, the flow out of the bathtub would exceed the inflow, and as a result would slowly move down toward the equilibrium level. This then represents a stabilizing or negative feedback loop. Let's also consider an amplifying or positive feedback loop. Earlier in the semester, we considered the balance of a bank account as a stock flow model. There, we represented the actual balance as a stock. We had an inflow corresponding to the interest that was earned on that balance. We also had an outflow corresponding to withdrawals. Generally, interest is a percentage of what the balance is. That is, we have a control from this stock to this flow. The greater the balance, the more interest earned. The smaller the balance, the less interest earned. We found the equilibrium by looking at when the incoming interest would be equal to the constant withdrawals that were being made. We can think about this, what would happen if we had more than the equilibrium balance. That would mean we were earning more interest than withdrawals that were being made each year. That interest would contribute to a larger overall balance and then would create further interest in the future. That is, the overall balance would tend to move away from the equilibrium point. Similarly, if we were in a situation where the balance was below the equilibrium level, that would mean that we were earning less interest than necessary to maintain the balance. And as we continued to make withdrawals, the overall balance would fall, again causing the stock level to move away from the equilibrium point, creating an amplifying feedback loop.